Yeah, well, I mean, this is a particularly exciting development. What we discovered for the first time is that when you look in detail at materials, the grains that make up the materials are not perfectly flat. And the conventional wisdom was that they were. So that instead of having grains that were like this, what we discovered was actually they move like this over a surface. And the implications of that are profound, because all materials' properties are determined by how the grains in materials connect together. Well, nanocrystalline copper is basically made up of copper grains that may have up to 1 million atoms apiece. They might be maybe 10 nanometers in size, 20 nanometers in size. But these will naturally emerge when you want to make small scale copper. And small scale copper is an integral part of the wires that make up the connections to devices that are in our computer chips today. Yes, I mean, for about 70 years ago, we could see atoms for the very first time, and this was through a method called transmission electron microscopy. And that allows you to look down through materials to see how the atoms and the grains actually sit in the material. But because you're looking down from the top, you don't get a proper view. It's almost like going over a densely packed village and you see a lot of houses, all the roofs look flat. But in actuality, if you can skate over the roofs, you'll see there are ridges and valleys in the roofs. What we've done is, instead of using TEM, we've actually gone and skated over the grains of a copper surface, and we found there's always ridges and valleys, and we were shocked. In fact, this was a revelation. And then we had to understand why they were the way they were, and we realized that the boundaries between the grains actually end up rotating, which causes the grains to rotate, which means you can never ever make a flat surface of copper and a whole other range of metal materials. Well, I mean, actually STM has been used, but never at this kind of resolution. We have a wonderful STM that operates at low temperatures. It gives you picometer resolution. That's a trillionth of a meter, actually. So it gives you incredible resolution. And so we can pick up even minute changes in the angles. Now, the angles are actually relatively large. They can be from 5 degrees to 10 degrees, and that's a very large change in angle. It actually means that the atoms are fundamentally misaligned going from one grain to the other. And this is a big impact for properties. If you look at, say, how electrons flow, electrons move along the atomic planes. And so when they go from one grain to the other, they go, oh my God, I have to change angle. And that causes resistance, which causes heat. And so if you're making wires in a computer, that means short battery life. Yes, I mean, I guess when looking at copper, we've now understood how it will impact other materials. And so we know that the boundary between grains, we know what determines the energies of those boundaries. But now we know for the first time that the energies of those boundaries are what we call anisotropic. How they point in space matters. And so rather than always pointing upwards, which is what you'd expect if everything was flat, you find that they're at an angle. And this applies to every material. And now what we have to do is basically do a trawl of all known materials and figure out which angles do different materials prefer. And so that's really opened up sort of a framework for how we're going to choose materials and then design materials going forward. Well, the plan next with this research is that we've looked at small angle grain boundaries, which is when there's just a small little tilt between the grains. We're looking at bigger ones now, and actually there's new surprises there as well. And it turns out actually, in addition to this, because of this twisting, there are also some strange rules regarding symmetry, which will be interesting as well. But we intend to move from copper to other metals. And then we also intend to look to see if we can put something into the copper to control the way it tilts. We know for a fact that the tilting requires some change in the way it sits on the surface, because these copper films and grains, they sit on a substrate. And so if we change the interaction between the substrate and the copper, we can change the tendency to tilt. And so that gives us a way to engineer materials in a way we didn't understand in the past. Well, I mean, in principle, it may allow us to engineer copper so it is flat. I mean, it naturally doesn't want to be flat, but can you engineer it to be flat, which would be super in terms of, mechanical, thermal, electrical properties. Also, we may, for some systems, want them to be actually quite bumpy, and we can engineer the bumpiness. But it means we're going to be able to tailor, for the first time, the boundaries between grains, And since that controls the communications between grains, it means we have a control of a wide range of properties. Well, I mean, certainly it will impact the device industries where they use these nanoscale films for contacts and for wires. But it also will probably impact coating industries because, in fact, the capacity of materials to adhere to metal, for instance, if you're making a stent, you know, you may want, you'll coat that in a particular metal, and then you want to make sure that that interaction is effective in the body. If you're making implants for medical devices, you want to make sure the grafting of that implant is effective. We use titanium a lot now at the moment. We haven't looked at titanium yet. What's titanium going to do? Will it affect the adhesion and the interaction of the metal with the other parts of the body? Those are all open questions at the moment.